Hello everyone, today we will present our re-implementation of SimpleNet, a simple network for image anomaly detection and localization. We applied the key idea of SimpleNet to our own custom paper cup dataset. First, imagine a small product factory. There is a camera on the production line, and we want to automatically detect defective products. However, normal product images are easy to collect, while defect images are rare and diverse. So our main question is, can we detect defects using only normal images? SimpleNet gives one possible answer to these questions. The task we focus on is anomaly detection and localization. Detection means deciding whether the whole image is normal or abnormal. Localization means finding where the abnormal region is located. This is not object detection, which predicts object classes and bounding boxes. Instead, anomaly localization highlights regions that deviate from normal patterns. So SimpleNet outputs an image level anomaly score and an anomaly heat map. Existing methods have several limitations. Restriction-based methods train a model to reconstruct normal images, but if the model reconstructs abnormal regions too well, defects can be missed. Image census-based methods create fake defects on images, but these fake defects may not look realistic. Embedding or memory-based methods can perform well, but they may require large memory or heavy computations. To reduce these problems, SimpleNet generates fake anomalies in feature space, not direct on images. The key idea of SimpleNet is simple. Instead of synthesizing scratches direct on the image, SimpleNet adds Gaussian noise the features extracted from normal images. These noisy features are treated as fake anomaly features. Then, the discriminator learns to distinguish normal features from fake anomaly features. So, SimpleNet learns a boundary between normal features and noisy fake anomaly features. The SimpleNet pipeline consists of 4 main modules. Each module has a simple rule. The feature extractor uses a pre-trained CNN to extract image features. The feature adapter transforms these features for the target dataset. The anomaly feature generator adds Gaussian noise to normal features and creates fake anomaly features. Finally, the discriminator decides whether each patch level feature looks normal. During inference, the noisy generator is removed. The remaining modules are used to generate the anomaly map. This slide briefly shows the training objective of SimpleNet. During training, SimpleNet compares a normal feature Q and a fake anomaly feature Q-, which is created by adding Gaussian noise. The discriminator outputs a normality score. The code is simple. Normal features should get higher scores, and fake anomaly features should get lower scores. During inference, we do not add noise. We convert the normality score into an anomaly score by taking the negative value. So lower normality means higher anomaly score. In the paper, the authors mainly use industrial datasets such as NVTech AD. However, we wanted to test whether SimpleNet also works on a dataset we created ourselves. So we created a custom white paper cup dataset. We took the photos in our square table tennis room and we used a navy background. For training, we used only normal images. For testing, we used both normal images and anomaly images that we created ourselves. Our dataset contains 96 normal training images, 24 normal test images, and 58 anomaly test images. We created 7 anomaly types: Merkle, ice cream, tap, hole, crumple light, crumple heavy, and upside down. The important point is that these anomaly images were not used during training. The model learned only from normal images, and anomaly images were used only during testing. We re-implemented the core structure of SimpleNet in Google Colab. Our goal was not to perfectly reproduce every detail of the paper. Instead, our goal was to apply the core idea of SimpleNet to our custom cup dataset. We used wide ResNet 50 as the backbone and used features from Layer 2 and Layer 3. The feature adapter was implemented as a one-layer fully connected layer. The Gaussian noise scale was set to sigma 0.015. The discriminator was implemented as a two-layer MRP. We first trained the model for 20 epochs and then increased it to 50 epochs. We preserved the core SimpliNet follow, pre-trained standard features, feature adapter, Gaussian noise, fake anomaly generation, and discriminator training, and we evaluated every heat maps and image level scores because our dataset has no fixed level masks. The table presents a comparison of the experimental environments used in previous research and in our experiment. This slide shows the qualitative result after 50 epochs. Each result contains the original image, the anomaly map, and the overlay. In the heat map, red and yellow regions indicate high anomaly scores. For local anomalies such as Merkle, tape, ice cream, and hole, the anomaly regions were highlighted quite well. For clumped or upside-down curves, the anomaly is more global, so the heat map tends to spread over a wider area. Next, we compare the result between 20 epochs and 50 epochs. At epoch 20, the maximum score of anomaly images was 1.351, and some anomaly images had lower scores than this value. This means there was still some overlap between normal and anomaly scores. At epoch 50, the maximum normal score decreased to 0.868. Also, every anomaly category had a minimum score higher than this value. Therefore, we used the 50 epoch model for the final analysis. This slide shows the final quantitative result. In the histogram on the left, normal images are clustered in a lower score range, while anomaly images are distributed in higher score ranges. This shows that the final model separates normal and normal images well in our test set. In the bar chart on the right, the normal category good has the lowest mean score. All anomaly categories have higher mean scores than normal. We also observed that crumpled heavy has a higher score than crumpled light, so the score tends to reflect visual severity to some extent. Of course, our experiment has some limitations. First, the dataset was captured in a controlled environment. The background, lighting, and camera position were relatively stable, so we did not test strong real-world variation. Second, the dataset size was small. We used 96 normal training images and 58 anomaly test images, so more samples are needed for stronger validation. Third, we did not create pixel-level ground truth masks. Therefore, we could not quantitatively evaluate the exact localization accuracy of the heat map. Further validation is needed in more complex real-world environments. To conclude, SimpliNet starts from a simple question. Can we detect anomalies using only normal images? It creates fake anomaly features by adding Gaussian noise to normal features and trains a discriminator to separate them from normal features. We re-implemented this core idea in Google Colab and applied it to our custom paper-cup dataset. As a result, even without using real anomaly images during training, we obtained meaningful anomaly heat maps. In summary, SimpliNet is a practical approach for anomaly detection using normal data and feature space noise. Our experiment shows the possibility of detecting anomalies using only normal data, even a custom dataset. Thank you for listening.